On the left, a standard security scan reports 0 vulnerabilities. On the right, a network monitor logs an active outbound connection to a malicious IP. The malware targets the developer's local workstation, compromising the environment used to write and deploy code. Once the infection routine is complete, the Trojan completely vanishes, leaving absolutely no trace behind in the local file system. Manual reviews of project directories and manifest files will show nothing suspicious to the developer. Standard defensive tools are blind to this specific attack because the malware deletes its own footprints as it executes. Axios is a foundational HTTP client. It is the tool programmers use to connect apps to the internet. The package handles 100 million weekly downloads, acting as a central hub for data requests across millions of applications. Because Axios is a standard building block for frameworks like React, Vue, and Angular, it is a high-value target for supply chain poisoning. Attackers successfully published 2 poisoned versions to the npm registry, Axios 1.14.1 and Axios 0.30.4. The high volume of downloads turned these poisoned packages into an automated blast radius across global developer pipelines. How can an attacker compromise a massive open-source project without triggering a single alarm in the source code repository? By separating code from distribution, the official GitHub repository remains clean, while the npm registry track receives a malicious payload. Compromised maintainer credentials let attackers bypass GitHub entirely, publishing directly to npm. These malicious Axios packages injected an obscure dependency called plain crypto.js version 4.2.1. This new dependency is invisible when reviewing the actual Axios source code. The phantom package is never actually imported or called by the application's logic. The attackers exploited the operational gap between source code visibility and package distribution to smuggle in a dormant threat. Post-install script line executes automatically during the installation process. When a developer or a build server runs the standard npm install command, the environment begins resolving dependencies. This automated process triggers the lifecycle hook, executing the setup.js file without any manual intervention. The script is an obfuscated dropper designed to probe the host machine's internal architecture. The dropper identifies whether the system is macOS, Linux, or Windows to pull the corresponding remote access Trojan payload. The act of installing dependencies, rather than running the application, is the trigger that compromises the system. Security teams must determine if the end users of the web application are at risk. The infection is contained within the build environment, keeping the client browser safe. Inside the infected zone, the Trojan scans local storage and memory, extracting sensitive environment variables like cloud keys and npm tokens. These secrets are exfiltrated to the attacker's domain, sfrclak.com. Because the Trojan lives in the install step, end users loading the compiled app in a browser are insulated from the malware. This is a pivot maneuver. The attacker steals infrastructure credentials today to backdoor more secure systems in the future. If the infection is active, why does the environment still pass an npm audit? The code is designed to be self-erasing. Once the Trojan is deployed, the malware destroys its own tracks. The final phase of the script is an automated cleanup routine. Within the directory tree, the setup.js file vanishes. Simultaneously, the package.json file deletes the malicious script lines it just used. The manifest file then rewrites its own structure to mimic a completely benign package. This self-editing mechanism leaves no malicious code for a human or a machine to find. Vulnerability scanners fail because the malware deletes the evidence of its own existence the moment the infection is complete. Because the manifest is scrubbed, defenders must look outside the source code for evidence of the breach. Engineering teams need to pivot from static code analysis to reviewing network telemetry and temporary operating system files. These are the primary indicators of compromise. Teams should search for traffic to the domain sfrclak.com, the IP address 142.11.206.73, and the presence of these specific OS files. The most definitive proof is found by verifying the SHA-256 checksums of the downloaded package files against known malicious signatures. Detecting this threat requires moving past application security tools and focusing on endpoint detection and network response. The risk applies to any machine or pipeline that installed the affected Axios or plain crypto.js versions with scripts enabled. To secure the environment, you must immediately sever trust and revoke all access for the compromised source machines. Any exposed machine must be treated as fully compromised by an interactive human attacker. You must rotate every secret, API key, and signing key that was present in the build environment during the time of installation. Modern supply chain security requires defending the deployment pipeline as fiercely as the product itself. The tools used to build software have become the primary targets.